The system that we're considering here should be only the beam, which is this diagonal looking shape here. So when we consider the forces on this beam, we're going to have the tension due to the cable, which is T sub C, the tension due to the rope, which is T sub R, the mass or the weight of the beam at halfway up, which is mg, and then we have the vertical and horizontal forces from the hinge that are identified as F sub V and F sub H. And if we consider this to be our pivot point, and now we apply the rules for equilibrium. You can start with any one you want. You can start with in the x direction, y direction, or torques. So let's go ahead and start with the torques and say that the sum of the torques about our pivot point P is going to give us, notice that if I consider P to be my pivot point, then I eliminate F sub V and F sub H as contributors to the pivot point. So we're going to have T sub C, and the distance from the perpendicular of T sub C to the pivot point is A. So we're going to have T sub C times A. That's going to give us one torque, and it's positive, right, because it's going to give us a counterclockwise rotation. Then we're going to have T sub R, and T sub R will give us a clockwise rotation, so that's going to be minus T sub R, and the vertical distance from where T sub R is pointing to the pivot point is B, so that's going to give times B. And then we have the weight of the beam, which is mg. It's pointing in a clockwise rotation, so that's going to be another minus. And its vertical distance from where mg is pointing to the pivot point is 1/2 B, and the sum of all of those torques has to equal 0 if it's in equilibrium. And now, if we consider the sum of the forces in the y direction, we get that the F sub V minus mg minus T sub R has to equal 0. And if we do the sum of the forces in the x direction, we get F sub H minus T sub C equals 0. And now we have applied the laws of equilibrium. So we have some unknowns now that we need to take care of. And note, since the system is in equilibrium, that means there's no movement, then the tension in the rope has to equal the big mass. So TR has to equal big M G because of the equilibrium conditions. And we know that this is going to be 430 kilograms times 9.8 meters per second squared. And another thing we can say F sub H equals F sub H equals T sub C, and we can see if that helps us down the road. So let's solve from this first equation. Let's solve for TC. TC is going to equal 1/2 mgb plus T sub RB over A, and we know that T sub R is big mg, so this is 1/2 mgb plus big mgb over A. And if we factor out the GB over A, we get big M plus 1/2 little m. All of these values we know, so we can find out that TC equals 9.8 meters per second squared, B, which is 2.5 meters, A, which is 1.9 meters, big M, which is 430 kilograms, and 1/2 times little m, which is 85 kilograms. And if we plug all of this in, we get 6093 newtons, or approximately 6100 newtons. And now we go back to part B. In part B, we're asked to find the components of the net force from the hinge. So notice that F sub H equals T sub C, which in this case it's 6093 newtons. And if we consider the sum of the forces in the y directions, then F sub V equals little mg plus T sub R, which is going to be little mg plus big mg. And this is the same as little m plus big M times G, which is 85 kilograms plus 430 kilograms times 9.8 meters per second squared, or 5047 newtons. So now we can say that F from the hinge is going to equal 6093 newtons I hat plus 5047 newtons J hat, which means F sub hinge, forgot the end, is going to equal square root of 6093 newtons squared plus 5047 newtons squared, or about approximately 7900 newtons. Which is, well, if you know this, much greater than the weight of the safe, which is combined weight of the safe and the beam, which is 5047.